Good afternoon, everybody. Let's get started. For announcements, the exam will be on Wednesday. That's exam 1, Wednesday the 12th. That exam will be held during class, plus 30 minutes grace period to submit your exam. So take a look at the announcement that I sent out via Canvas. You'll download the exam. It looks like an assignment. You can print out the exam, work on the paper, scan it, upload it. You can work on a tablet, however you want to work to show your work and to show your answers. So take a look at those instructions that I sent out via a Canvas announcement. There are review problems on Canvas and also practice problems on Canvas. Those are kind of two different sections there. So take a look at those. Homework 3 is due tomorrow. So if you have any questions about the Thévenin equivalent circuit material that we covered, stop by office hours today and we can talk about those. My office hours will be right after class. So just stick around on this Zoom session and we can chat. So I wanted to continue just a little bit with the Thévenin equivalent circuit topic. Last time we talked about Thévenin equivalence, how to calculate the Thévenin equivalent circuit, and then maximum power transfer, right? If you want to maximize power transferred from a realistic source to a load, you make that load's resistance equal the Thévenin resistance of the source. So let's give this a shot. Let's do a clicker question. We're going to get started with that. Let's get the clicker app started up here. Okay. So you have this circuit, and it's a current source, a resistor, and then you have a couple terminals here. And you want to find the Thévenin equivalent circuit between terminals A and B. And so what is that? What VT and what RT would you assign to this this model in the upper right to have the Thévenin equivalent of the circuit on the left? Give that a shot. So remember that the Thévenin equivalent consists of the Thévenin voltage and the Thévenin resistance. The Thévenin voltage is the open circuit voltage between terminals A and B in this case. Don't connect anything to A and B, figure out the voltage across A and B. That's the Thévenin voltage. The Thévenin resistance, you can calculate using short circuit current and open circuit voltage, or if you have only independent sources, you can zero out the sources, calculate the equivalent resistance between the terminals. Okay, so to calculate the Thévenin equivalent of the circuit on the left, let's start with calculating VT, the Thévenin voltage. Thévenin voltage is the open circuit voltage between terminals A and B if you don't connect anything to those terminals. Right? So what is that voltage? Well, I know I have 0 amps going out of terminal A because it's not connected to anything. So all of the current source current, that 5 amps, must go down through the 15 ohm resistor. I'm doing a mental Kirchhoff's current law calculation on that top node there. So we have 5 amps coming down. Ohm's law says the voltage across that resistor with this polarity is 5 times 15. That's 75 volts. And so VOC must be 75 volts. To calculate the Thévenin resistance, since we only have, well, an independent source here, there's no dependent source. You cannot do this technique I'm talking about when you have a dependent source or a diamond in your circuit. So what I can do is I can redraw this circuit. I can zero out that source, make that source 0 amps. So to make that source 0 amps, I can call that an open, like I have here, and then calculate the equivalent resistance between terminals A and B. There's just one resistor left, or that resistor is the equivalent resistance between A and B. So Req is 15 ohms. We get D, so that's the answer. All right, so if you'd like to talk more about this problem or similar problems, stop by after class at office hours and we can chat about Thévenin equivalent circuits. All right. So we've reached a kind of a mini milestone in the course, and I want to bring up the roadmap. So this is the roadmap that I talked about that lists all the major topics of the course. And I like to show every once in a while where we are in these topics. We covered basic electrical theory. This is a volt, this is an amp, this is a watt. Um, and we talked about analysis of DC circuits, Kirchhoff's laws, node voltage analysis, Thévenin equivalence. We just finished up. So now we're going to move on to transient circuits or transient circuit analysis, or sometimes called transient responses of circuits. And so these circuits, the interesting ones anyway, have capacitors and or inductors in the circuit, along with resistors and sources. And what we're usually studying and what we're going to study here is what happens to the voltages and the currents in a circuit when you have a sudden change in the circuit. So you have that sudden change could be a switch turning on, a source being connected, a source being disconnected. There's some sudden change, and then you get a response that varies over time. Many of the responses vary over time, and they have this exponential change. So we're going to talk about that. Up until now, if you turned on and off a source in a DC circuit, you would get these step changes, right? You wouldn't have much interesting happen at that step change or at that sudden change. You just get changes of voltages and currents instantaneously if you have only resistances in your circuit, theoretically. Okay, so let's start in on transient circuits, and we're going to talk about capacitors and inductors to start out with. So let's talk about capacitors and inductors. Oh, there we go. Trying to get my arrow up here. So someone asks about the exam material. So the exam material ends at the Thévenin equivalent circuit material and maximum power transfer. So this is new material beyond the exam. This will be on exam 2. Okay, so let's talk about capacitors and inductors. So capacitors and inductors are considered energy storage elements. Capacitors, the mechanism in capacitors that stores energy is the electric field. In an inductor, it's a magnetic field. And although they are energy storage elements, you can think of them that way, we often use them for their current versus voltage characteristics. And the reason we do that is because you get you can implement circuits like electrical filters that allow some signals to pass and other signals at different frequencies to get blocked by the filter. You can perform signal conditioning. You can remove certain bands of noise from a signal, from a voltage or a current, and you can actually use capacitors and inductors in circuits that create waveforms, so create sine waves or create square waves, and the capacitor and inductor values can control the frequency of those signals. Okay, so capacitors store energy using an electric field, and you've probably seen capacitors before. You have these in your lab kit. So these are electrolytic capacitors on the left. They kind of look like these cylinders with leads, 2 leads coming out the bottom. Some of these have a lead coming out the bottom, a lead coming out of the top. There's various configurations of those. In the lower right, here are some capacitors. You have these, here's a ceramic capacitor, low cost, common capacitor. Here's a tantalum capacitor, probably just a different material, handles different capacitance per volume and different voltages. Here's some chip capacitors, surface mount capacitors. So if you see these packages, you're probably looking at a capacitor. For inductors, inductors store energy in the form of their magnetic field or using their magnetic field. So they create a magnetic field, and that's how the energy is stored. Inductors are coils of wires. So here's a coil of wire, nothing in the center. That's an inductor of a certain inductance. Here's another inductor. It looks the same, but it has a core, right? So that core might be some kind of ferrite material or ferrous material. Other shapes of inductors, here is a toroid inductor. That can give you fairly high inductance values. It constrains most of the magnetic field to inside that toroid core, which might be a ferrite material. Here's like a bobbin inductor, usually surface mount. Here's an inductor that looks like a resistor, but that's an inductor. And here are a couple other surface mount inductors. So different shapes of those, but they're all based on generally coils of a conductor or a wire. Okay, so let's start with capacitors and talk about capacitors. So I'm going to show you one way to build a capacitor or represent a capacitor. There are other shapes, other geometries, but if you take a conducting plate, so here's a metal plate, and you put another plate parallel to that conducting plate, so two of the same plates, and you separate those metal plates by an insulator, and you connect a couple wires. You have created a capacitor. In fact, the schematic symbol for a capacitor looks a lot like this. Here's the schematic symbol for a capacitor. So we care a lot usually about the current versus voltage relationship here, right? Just like Ohm's law related for a resistor, voltage versus current, we're going to take a look at, well, how does voltage relate to current for a capacitor? And then we're going to make use of that in future circuits. So if I have this capacitor, initially 0 volts across it, and then say I connect maybe a power supply, and I start turning up the voltage in the positive direction. What's going to happen is I'm going to have charges accumulate on the surface of these metal plates, these conducting plates, and an electric field is going to form across this insulator. It's usually a dielectric material. And so we're going to have this electric field. That's a mechanism which causes this capacitor to store energy. The capacitance of a capacitor is specified in farads. Usually in typical components in lab, you have microfarads, nanofarads, picofarads. Typical component sizes, you may have a 220 microfarad capacitor or 1,000 picofarad capacitor, something like that. And what you can do is you can relate the charge stored by the capacitor to that capacitance value and the voltage. And Q is equal to C times V. Okay, so C is the capacitance. That capacitance is related to a few things. In this flat parallel plate example here, the area of those plates and the distance between those plates affects the capacitance. The dielectric constant of the insulator in between determines the capacitance value. Capacitance is epsilon A over D. Epsilon is the dielectric constant. We're not going to get into that, but the physical geometry and the materials in the capacitor determine the capacitance. What we usually care about in circuits is you look at the capacitor, you have a value, or you calculate a value that you need, and you create a capacitance using one or more capacitors to get what you need. But Q is equal to C times V. The charge stored is equal to that capacitance value times the voltage across the capacitance. Okay. Well, we want to derive the current versus voltage relationship. So let's take the derivative of Q, right? So take the derivative, both sides of this equation with respect to time, dq dt and dv dt on the right, right? Because we're assuming both Q and V will change with time. C is a constant. The distance between plates, this plate area, the dielectric constant doesn't change with time, so it comes out of that derivative. Well, dq dt from the first day of class is current. So I then is equal to C dv dt. So this is the equation we're going to use a lot when we're working with capacitors. So the current is equal to C, the capacitance, times the derivative of voltage. Okay, so this current I, if you were to measure the current I in this wire, and you have a constant voltage across the capacitor, if V is a constant, dV dt is zero. So the current will be zero. Well, that kind of makes sense. Well, it does make sense because you have an insulator between two wires, even though you have these metal plates. So if the voltage is not changing, the current is going to be zero. But what happens if you change that voltage, you're going to get, as you change the voltage, the charge that's stored in the capacitor is going to increase and decrease and increase and decrease, as you raise and lower the voltage according to Q is equal to C times V. Well, as that charge changes, that means either current's flowing down to charge the positive charge, to add positive charges to this capacitor, or if the voltage is falling, right, the current, the charge is leaving and the current in the wire is going the other direction. So that's why when the voltage changes, right, the charge is changing on the capacitor, it looks like you have current. There's actually no charge crossing the insulator here, right? There's no actual flow of current through the capacitor, but since charge is building up and going away inside this capacitor's package, it looks like there's current flowing. Well, there is current flowing through the wire, and that current is C dV dt. Okay. This is the derivative form of the relationship between current and voltage. If I have voltage and I want to calculate current, this is what I'd use. If I know the current, if I know I, and I want to know the voltage, then I have to integrate both sides of this equation. And then the form of the equation looks like this. So I have to have some starting point in time. So I have some point in time where I have some voltage, V of T sub 0, T naught. And so then the voltage is 1 over C, the integral from that initial voltage to some time T, this current time where I'm interested in the voltage, times the integral of current with respect to time, d time, right? I'm using this tau as an integration variable here, just because I have these other t's in the equation. Tau is just a variable of integration for time. So I'm going to integrate current from some time to some future time, or some past time to some present time, multiply by 1 over c, and then add in the voltage at that initial time. Okay, we'll take a look at that. Okay, so let's work an example, in fact, now. Let's move over to the whiteboard. So let's work a capacitor example. Let's suppose that you have a capacitor in lab, and it's on the bench, and you're going to connect a function generator that creates sine waves to this capacitor. So you're going to apply a voltage, V of t. It's an AC voltage. Let's assume it's a sinusoid. And so let's write a sinusoid. We'll talk more about sinusoids later, but we'll get the idea here. So V of t is sine 10 to the 6th t, that's in radians per second, times seconds gives me radians as the argument of the sine. But you could create this sine wave 1 volt peak 10 to the 6th radians per second. You can convert that to hertz if you wanted, but that's the voltage you're going to apply to this capacitor in lab in this made up example here. Okay. And then let's suppose you want to figure, right? This is connected to something. Let's suppose you want to figure out what is the current I of t given that voltage. So find I of t. And you look at the package of the capacitor and it says C is equal to 10 microfarads. So it's a 10 microfarad capacitor. Okay. And so let's calculate this. So the relationship between current and voltage for a capacitor is I of t equals C dV dt. So that equals C, which is 10 microfarads, 10 times 10 to the negative sixth. Times the derivative of sine 10 to the sixth t. Okay, so you get what? 10 times 10 to the negative sixth times the derivative of sine 10 to the sixth t, which is 10 to the sixth cos 10 to the sixth t. So that's the derivative. So that equals, let's see, the 10 to the negative 6 times 10 to the 6, that cancels out. You get 10 cos 10 to the 6t. Okay, so that's I of t. So that's just a simple example of if you know the voltage, how do you calculate the current? This is how you would do that. But it shows a couple interesting things here. Notice that I've taken a sine function and I've converted it to a cosine function. So the voltage is a sine, the current is a cosine. And if you plot a sine versus a cosine, you'll notice that they're shifted in time, right? They're 90 degrees shifted in time. So you can implement a phase shift with a capacitor. Also notice this number that came out front when I took the derivative, this 10 to the sixth, that was dependent upon the frequency, right? This frequency here. And as I change that frequency, the number that comes out front, which winds up to be affecting the amplitude here, that frequency affects the amplitude of the current. So that's where the filter function is going to come in. We'll see that you get different currents based on, in this case, what the frequency of that sine wave is. Right? So I wanted to point that out with this simple example. Okay. So this is the derivative form of I versus V. If you want V versus I, then you use the integral form. And someone asked in the chat, so that voltage V of T naught is not included in the integral. That's correct. So that everything to the right of d tau in that equation is not in the integral. Okay, so all right, then in fact, let me bring that up now. Okay, so what I was mentioning just now is that this V of T naught, yeah, that's outside the integral there. Okay, all right, so that's a quick introduction or overview because I'm sure you've seen capacitors before. Let's jump into inductors. Okay, so to make an inductor, it's really easy. One form of an inductor is just a coil of wire. And so if you take a coil of wire like this and you define a current and you cause some current, let's just make it a positive current, to flow through this wire. what's going to happen is you're going to create a magnetic field. So if you've ever, wrapped a coil of wire around a nail, connected it to some power supply and, tried to pick up metal objects, that's exactly what this is. So this is, you've created the magnetic field with kind of this shape, these shaped lines here, these field lines. So the schematic symbol of an inductor is this. It looks a lot like that coil. And let's define a current and a voltage across this inductor. So current through the inductor, voltage across the inductor here. Okay. So I think it's pretty intuitive that if you change the current through this wire, let's say from 1 amp to 2 amps to 3 amps, you're increasing this magnetic field strength, right? If you decrease the current through that wire, you're going to decrease that magnetic field, okay? And, think about if you've ever talked to anybody or read about how a generator works. If you have a coil of wire in a time varying magnetic field, then you're going to induce a voltage. That's how a generator works. Okay. In this case, you're considering the magnetic field that this coil is creating by itself, not created by maybe some separate magnet, separate either permanent or electromagnet, but you're just considering the magnetic field that's generated by the current through this coil. And it turns out that a change of current will induce a voltage that opposes that change of current. So if I try to increase this current, the magnetic field changes, and a changing magnetic field, if a coil has a changing magnetic field through it, you're going to get a voltage induced, and actually that voltage will oppose that change of current. So if I try to increase I, I'm going to get a voltage that opposes that change or pushes back against that change. If I try to decrease I, I'm going to get a voltage that opposes that change, which means it's going to try to keep the current flowing. Okay. So we're dealing with Faraday's law and Lenz's law here. And so if you want to read more about those, but from a circuit's perspective, we're going to look at V versus I or I versus V. We're characterizing the inductance of that coil with this variable L, and that's in units of henries. We usually deal in lab with inductors that have microhenry or nanohenry values, maybe millihenry for big inductors, but and the relationship between voltage and current is this: V is equal to L di dt. Okay. So where does L come from? L is related to, if you have this cylindrical coil here, you can look up, I think it's Wheeler's relationship, Wheeler's law, Wheeler's formula, it's called something like that. The number of turns, the diameter of the turns, the spacing of turns, all determines that inductance. And usually, well, in fixed inductors, you have a fixed inductance. You can build variable inductors, but let's say we have a fixed inductor here. That's going to be the same. So that's this L value for a given inductor. If I have a DC current flowing through this inductor, I have a constant magnetic field. That magnetic field is not changing through that coil, so you'd expect no voltage across that coil. And you see that if I is a constant, take the derivative of a constant, 0 times L is 0. Right, so if you just have a coil of wire, DC current flowing through, there's no voltage across that coil. Let's assume that wire has 0 resistance. Okay, but if I try to change the current, I try to ramp up from 2 amps to 3 amps, then that's going to give me a positive derivative here. Positive derivative times this positive inductance gives me a positive voltage. That means this voltage here is going to be positive, and it's going to oppose that change of current. It's going to push back against that current, try to keep it from changing. It's going to lose, but it's going to try. So that voltage will happen. If the current steadies out again to a DC value, the voltage goes back to 0. if I try to decrease the current, I get a negative derivative here. That voltage goes negative. Then I have a negative voltage with this polarity, or you could, if you want to visualize this with a positive polarity, the polarity switches, so positive would be on the bottom. So as this current is trying to decrease, this voltage is trying to keep that current flowing. Okay, it's trying to oppose that decrease of current. Okay, so that's the relationship we're going to work with a lot for inductors. This is the derivative form. If you have current, you want to calculate voltage, this is what you would use. If you have voltage and want to calculate current, then this is what you would use. So you have, you have maybe some time in the past, T naught, and you want to know what the current is at the present time, T. So you would say 1 over L times the integral from that time in the past to the current time, integrate voltage over time, right, over that time duration, that interval there. Tau is just a variable of integration. It means time, but I've already used T, so I don't want to use it again. And then plus the current at that initial time, T0, that time in the past. Okay, that I of T0 is outside of the integral here. All right. So let's take a look at an example. And let's use the integral form here. So let's switch over to the whiteboard. So let's do an inductor example. So let's suppose you set this up in lab, and it's not a very good idea to do this. I'll show you why, but let's do it anyway. Let's say you take a power supply and you set it to 10 volts, and you have an inductor. And that inductor has a value of 2 henries. That would be a big inductor, but let's make the math easy here, make the numbers easy. And I connect a switch. I put a switch between the positive of the 10 volt supply and the top of that inductor there. Right. So, and let's close this switch. Let's put a time on this. Let's close this switch at t equals 0 time. And let's see what happens with respect to voltage and current for this inductor. Okay, so we have voltage across that inductor, and here's current. Both versus time, they're going to change when that switch closes over time. And so let's find I of t. All right. So let's solve here. Let's apply the equation and figure out what's going to happen. Well, let me at the same time draw a graph here. So this is going to be V of t, the voltage versus time. And I'm also going to plot current versus time. Okay, and let's plot out what the voltage is. So before t equals 0, so this is time 0 right here, t equals 0, t equals 0. Before t equals 0, we have one end of the inductor left hanging. There's no current, there's no voltage, so V of t is 0. And then all of a sudden, I close this switch and I connect that 10-volt supply directly to the inductor, and the voltage instantaneously, theoretically, jumps up to 10 volts. Okay. And you could figure out, well, the current before t equals 0 is also 0, so we can put that there. All right, so let's calculate I of t. So I of t is equal to 1 over L. So we have the voltage, we want to find the current. We have to use the integral form of the equation. We're going to integrate from some time, and we're going to say, let's use time 0, because at time 0, we know what the voltage is, we know what the current is, right before time 0. So we're going to use 0 as our starting time here. And then we're going to integrate up to some time in the future past 0, time t. And we're going to integrate v of tau d tau plus the current at time 0. Right. So let's see what that looks like. I of t equals 1 over L, 1 over 2, times the integral 0 to t of v of tau, right? That's v versus time, between 0 and some time t. Well, that's 10 volts, d tau, right? Plus I of 0. Well, I of 0 is 0. There's no current flowing at time 0, so plus 0. Okay, so we could say this is 1/2. So if I integrate 10, I get 10 tau, with tau evaluated at 0 and t plus 0. So this is equal to 1/2 times 10 times t minus 0. So I get 1/2 10 t minus 0 equals 5t. Okay, so that's the math result, calculus result here. Okay, so right at t equals 0, you get this ramp of current, this linear ramp with slope 5. So I start at 0. At t equals 0, I get 0, and then I get this linear ramp going up. Okay. And in fact, if you look at this at 1 second, I have, what, 5 amps. Okay, so fine, right? That doesn't look all that bad. I get this ramp function of current. I close the switch, I get this ramp current. The reason I said not to do this is that, well, if you leave that switch closed, at 1 second you have 5 amps, at 2 seconds you have 10 amps, at 3 seconds you have 15 amps. This current just keeps climbing, and something's got to give, right? Something practical has to give here. You can't keep going up to infinity current. So what'll happen is either this power supply will hit its current limit, okay, and the current will level off. Let's say if you have a current limit set, or if this power supply has a really high current capacity, then this inductor is going to probably burn out if it's a kind of a small inductor. The wire does have resistance. If it's made of very thin wire, that wire is going to get hot when you put too much current through it. It's basically going to look like a small valued resistor. Eventually, the power gets to the point where you you burn out the coils of wire, you burn out the wire. So either if this is if this is a kind of hefty gauge wire inductor, then you probably hit the current limit of the power supply, um, or you burn out this wire. So something probably unintended is going to happen if you do this in lab. Okay. But there is a practical case where this is a simplified version of it, but where this might be useful if you want to generate a really big voltage. And let me show you why. If let's say at time equals 1 second, right? This is 1 second right here. 1 second at that point. Let's suppose I open this switch. Okay, so I open the switch and the current as I open that switch just falls to 0 like that, right? Because no current can flow through an open switch. Well, now if I look at the equation V is equal to L di dt to see what's happening with voltage, well, I've just rapidly shut off this voltage. In this case, this is a negative infinity slope here in theory, right? Negative infinity. So di dt is trying to be negative infinity. And so you're going to get this like delta function that goes down. You're going to get this big negative voltage. It tries to go to negative infinity. It's not going to work because other practical things are going to happen. So if you try to open up the switch, this, as the current shuts off, V is equal to L di dt, this voltage becomes very large, negative. If you run a KVL around here, that very large voltage shows up across the switch. And what's probably going to happen is you're going to get a little arc here. You're going to get a spark. You're going to ionize the air as the contacts try to separate. And that's how the energy is going to be dissipated. So, but nonetheless, you do get a big negative voltage when you try to shut off current rapidly. Okay, and I mentioned, well, that there's a good reason to do this. Well, let's suppose you do something like this. You take, I'm going to put a little resistor in here to show that there's some resistance in this circuit. But you take the same circuit with an inductor and you put another inductor next to it and magnetically couple those. That's called a transformer. We're not going to talk about transformers, but you can probably get the idea. If I have a turns ratio of many on the right and few turns on the left, I can actually step up the voltage. So as I got this big negative voltage when I opened the switch here, I'm going to even step up that voltage with this transformer. And if I have a couple contacts here, then I could get a spark here, right? So I'll get a spark there. And this is how some ignition systems work. So if you have like spark plugs in a car, in light aircraft, they use what are called magnetos. So there's a current flowing and there are points that separate. They cause a rapid change in current. You get a big voltage and you get a spark at the spark plugs. So that's one way you can generate a big voltage using an inductor and V equals L di dt. Okay. All right. So the takeaways here are, this is the relationship between current and voltage. We did an example using the integral form of that equation. And then I showed you a practical implication of shutting off that current quickly. And that's a V equals L di dt. This form of the equation shows you how you get that big voltage right there. All right. Okay. So those are that's the fundamental. Those are the fundamentals of how capacitors and inductors work. And so now we're going to start talking about the circuits that you use, that you create with capacitors and inductors. We'll talk a little bit about that. So someone says, aren't capacitors used for defibrillation, like shocking the heart? There are various ways to create a big voltage there are ways to use a capacitor. I'm not sure exactly how the defibrillators work, but yeah, you can also create big voltages. One approach is using capacitors too. Mhm. Okay. Yeah, you don't want to mess with big inductances and shutting off current rapidly with big inductor values. That you can shock yourself fairly easily and fairly strongly with those. So you got to be careful. With the inductors you're using in lab, I think you're using an inductor. We have or used at least used to have a 3.9 millihenry inductor, microhenry inductor. It's pretty small, so you won't have problems with that. Okay, so let's talk about the circuits you're going to be analyzing and creating in lab. Okay, let's talk about first order circuits. You might have covered some of this in your physics class, but we're going to talk about the intro, kind of the review again. So let's talk about first order circuits. And we're going to start with an RC circuit example. But let me say in general, circuits that only have resistors, they behave they have a pretty uninteresting response, I think. In circuits with only resistors, when a source is turned on or a switch position is changed or there's some otherwise rapid sudden change in the circuit, voltages and currents change instantaneously in theory. In circuits with capacitors, inductors, and resistors, when a source is turned on or a switch position is changed, or there's, you pull a resistor out or you plug a resistor in, there's some sudden change. Some of the voltages and currents do not change instantaneously. And that interesting change, I call it, is called the transient response. The transient response, when I say that, is the time varying change of a voltage or a current that results from that sudden change in the circuit. So I may have some voltages and some currents in the circuit where I pull a resistor out, I turn a switch on, I turn a source on, I turn a source off, something like that. I get this transient response. So you're going to see when you write KVL and KCL and other equations in these circuits, you're going to get equations with derivatives. Because you saw that I versus V and V versus I for capacitors and inductors have integrals or derivatives. And so if you have, in general, an RLC circuit, the transient response, that time varying response is going to look like this. It's going to look like a second order differential equation. So here, this voltage is represented by a second order differential equation that might have resulted from some KVL or KCL equation. Okay. If you have only R's and L's or R's and C's, right, an RL or an RC circuit, you're going to wind up with a first order differential equation. So this is a first order circuit. And so you're going to have not the second derivative like we have on the left, but only the first derivative. You're going to get equations of this form: A dV dt plus B times V of t equals D, some other constant. Okay, and you can replace V with I. We're going to see I changes according to this first order differential equation as well. Okay, so we're gonna focus on first order circuits, RC and RL circuits. Okay. All right. So I've hit the end of class for today. We'll pick this up after the exam. Don't forget that there is an exam on Wednesday. I did see some emails about that, about some schedule conflicts. I'll get to those later today. We'll resolve that. So see the announcement that I sent out via Canvas, and also see Canvas for the upcoming assignments. You have a homework due tomorrow. Thanks for joining class. If you'd like to join office hours, then stick around on this Zoom session. If not, I'll see you next time. Have a great night.